Welcome to our quantum deep dive.
Great to be here.
Today we're diving deep into kwantumverbesserte Convex-Optimierung. That's quantum-enhanced convex optimization, an essay by Jorgo Schneeppert.
Yes, and it's a fascinating topic. We're looking at how quantum computing, this really cutting-edge field, might just revolutionize convex optimization.
Which is already incredibly important, right?
Absolutely. What's truly fundamental, and Schneeppert really lays this out, is just how powerful convex optimization is. I mean, it's the engine behind so much tech.
Like machine learning algorithms.
Exactly. Or complex financial market calculations, logistics planning, you name it. And its core strength. Well, if you find a good solution, a local minimum, you've actually found the best solution. The global one.
It's like searching for the bottom of a smooth bowl.
Sure.
Once you're there, that's it. Lowest point.
Precisely. No hidden deeper valleys to get stuck in.
And that one valley landscape makes the whole optimization process so much more reliable. We see it, like you said, in machine learning fine-tuning algorithms. It lets us reliably teach a machine without it getting stuck on a bad interpretation of the data.
And in logistics, too, finding the most efficient delivery routes. Or finance.
Oh yeah, finance balancing profit against risk. Convex optimization gives that mathematical backbone to sort of balance the greed and fear in investing.
It really does. But, and this is where Schneeppert pivots, when the problems get huge. Massive data sets, really high-dimensional scenarios. Classical computers start to, struggle.
You can hit a wall.
Exactly. And that's the opening for exploring quantum computing.
Okay, so let's talk quantum.
Well, as Schneeppert explains, instead of the usual zeros and couple ones, the bits, quantum computers use qubits.
And these qubits, they're different.
Very different. They can exist in multiple states at once. Think of that light switch again. But it's not just on or off. It's kind of somewhere in between. Dimmed, maybe?
That's superposition, right?
That's superposition. And it allows quantum computers to explore a huge number of possibilities all at the same time.
Right. So a classical computer goes step by step, one calculation after another.
But a quantum computer could, potentially, look at many solutions simultaneously.
That's the idea.
Okay. So Schneeppert's essay is our guide today. Our mission, then, is to understand how these quantum algorithms might supercharge convex optimization. What are the benefits? And importantly, what are the hurdles still in the way?
Precisely. And Schneeppert builds this up carefully. He starts with the basics of convex optimization, then introduces quantum computing concepts.
Yeah.
You really need to get a handle on both sides.
To see how they might fit together. Makes sense.
Yeah.
So Schneeppert first defines what convex really means in this context. It's about the objective function, the thing you're optimizing, having that smooth, bowl-like shape.
And the solution space, the set of possible answers, needs to be convex too. Which basically means if you take any two valid solutions, anything in between them is also valid.
He gives the math, of course, but the key takeaway is that guarantee. There's one single best solution to find. And the essay really emphasizes this convexity is what makes classical optimizations so useful. That guarantee plus efficient classical algorithms like gradient descent.
Which is like rolling downhill to find the bottom.
Kind of, yeah. That combination makes it incredibly practical for many problems.
Schneeppert then walks through those key areas we mentioned: machine learning, logistics, finance. It's actually amazing how this one mathematical idea supports such different fields.
It is. But then, as Schneeppert shifts to how we solve these problems classically, you start seeing the limits.
Right. Those gradient descent methods, while good, can get really slow with today's huge data sets.
Or just problems with loads of variables. Calculating that downhill direction over and over gets computationally really expensive.
Okay, so that naturally leads us into quantum computing basics.
Yes. Schneeppert explains the shift from bits to qubits, and that key idea, superposition. A qubit being both 0 and 1 at the same time. Which
means a quantum computer with, say, 50 qubits can handle vastly more information than a classical one with 50 bits.
Exponentially more, potentially. And Schneeppert also brings in entanglement.
Ah, yes, the spooky action at a distance.
Yeah. It's like two qubits become linked. Knowing the state of one instantly tells you something about the other, no matter how far apart. It's weird, but powerful.
And these quantum effects, superposition, entanglement, they're the foundation for algorithms that could, for certain problems, be dramatically faster than anything classical.
Schnepphat points to landmarks like Shor's algorithm for factoring,
which breaks common encryption.
and Grover's for searching. Now, these aren't directly for convex optimization, but they show the kind of speed-up quantum can offer.
And as Schnepphat argues, optimization problems seem like a really promising area for quantum computers.
Definitely. That ability to explore many possibilities at once via superposition, that could be a total game changer for those huge, complex optimization tasks that choke classical machines.
He mentions specific algorithms.
He does. Things like QAOA, that's the quantum approximate optimization algorithm, often used for combinatorial problems, like finding the best combination of things.
Okay.
And HHL Harrow, Hasidim, Lloyd, which can, under the right circumstances, solve systems of linear equations incredibly fast.
And many convex optimization problems can somehow be related to linear equations, right?
Exactly. They can often be reformulated or involve solving such systems as a key step. So HHL is very relevant.
So the essay then connects these quantum algorithms back to convex optimization. It sounds like it's not just a simple plug-and-play situation.
No, not at all. It's more about creatively translating the convex optimization problem into a form that a quantum computer can, understand and hopefully solve faster.
Schnepphat points out something interesting there about Lagrange multipliers, a classical technique.
Yes. He notes a connection between those, which are used classically to handle constraints in optimization, and certain ideas in quantum mechanics about energy levels. It hints at maybe a deeper link between these fields than you'd first think.
Fascinating. But Schnepphat is also realistic, right? He talks about the hurdles.
Oh, absolutely. He discusses decoherence. That's where the environment noise basically messes up the delicate quantum states of the qubits, causes errors.
So you lose the quantum advantage.
Potentially, yes.
Yeah.
Which leads to the need for robust error correction. That's still a huge area of active research and development. It's not easy.
And scale is another issue he brings up.
Definitely. Today's quantum computers just don't have that many qubits, often not enough for the really big real-world optimization problems.
And some algorithms, like QAOA, have their own challenges.
Yeah, finding the best settings for QAOA itself can be a hard computational task. Plus, Schnepphat mentions the practical stuff, energy consumption, the sheer cost of building and running these machines. They're not desktop items yet.
No, definitely not. Okay, so moving to the core idea. Quantum-enhanced convex optimization. What are the theoretical advantages the Schnepphat details?
Well, he reiterates that potential for exponential speedups, especially with HHL for solving those linear systems. That's a big one, as linear systems pop up everywhere in convex problems.
But there are conditions, right? The system needs certain properties.
Yes, exactly. HHL works best if the system is sparse, meaning lots of zeros and well-conditioned, so it behaves predictably. Not all systems fit that bill.
Okay. And the other big advantage?
The inherent parallelism. Superposition lets the quantum computer explore, effectively, many potential solutions at the same time. This could mean major time savings, especially for problems with a vast number of possibilities.
Schnepphat also mentions how algorithms like QAOA can be applied.
Right, especially to combinatorial optimization like that delivery truck route problem, particularly when those problems can be approximated using convex techniques. He also mentions VQE.
Variational quantum eigensolver, used a lot in chemistry.
That's the one. It's another tool that researchers think could potentially be adapted for certain convex optimization tasks.
So, to make this less theoretical, Schnepphat gives some examples of applications.
He does. In machine learning, for instance, using quantum algorithms to potentially speed up training some models by handling the underlying math more efficiently.
And finance. Portfolio optimization.
Yes, exploring how QAOA might help optimize investment portfolios, especially those with really complex constraints or rules. And logistics, tackling those tough routing problems.
Even materials science.
Yeah, using quantum optimization to find the lowest energy shapes for molecules, which is key to designing new materials.
Schnepphat then kind of compares classical and quantum approaches, giving a balanced view.
Exactly. He acknowledges that classical algorithms are mature, scalable, and work perfectly well for many current problems. You don't need a quantum computer for everything. But for the really complex challenges, quantum methods offer that exciting potential for speed-ups and parallel processing. Though, again, he's clear about the current limits of the hardware noise, accuracy, just getting access to these machines.
So classical is the workhorse today, but quantum enhanced is this really promising frontier, especially for problems pushing classical limits.
That sums it up well.
The essay then digs a bit deeper into specific areas, like AI.
Yeah, Schnepphat discusses the potential for quantum algorithms not just to speed up training, but maybe even to explore more complex AI models than we currently can.
And in finance, he elaborates beyond portfolios.
He talks about faster, maybe more sophisticated risk management and investment optimization generally.
And Schnepphat mentions other fields too.
Briefly, yes. Designing new materials, optimizing energy grids, maybe speeding up drug discovery, improving logistics and transport networks, even contributing to better climate models.
Wow, the potential reach is pretty staggering, even if it's early days.
It really is.
But Schnepphat circles back to the challenges, doesn't he? He doesn't want us getting carried away.
No, he's very grounded. He revisits the limits of current quantum computers, the number of qubits, how long they can hold their quantum state reliably, which is called coherence time. It's often very short.
And the critical need for better error correction. You can't trust the result if noise is constantly disrupting things.
Absolutely essential. Overcoming noise is vital if these algorithms are going to be truly useful for complex, real-world optimization.
Looking ahead, though, Schnepphat seems optimistic.
He does offer an optimistic outlook for the future. He anticipates significant progress in the hardware, more qubits, better stability.
And better algorithms, too.
Yes, continued improvements in quantum algorithms specifically designed for optimization tasks.
He also mentions the synergy between quantum computing and machine learning.
Right, suggesting that future breakthroughs might come from combining these two powerful fields in new ways, like using ML to help design quantum algorithms or control quantum hardware.
And Schnepphat stresses collaboration.
He does. Tackling these big challenges needs people from physics, computer science, math, engineering, and all the different application areas working together.
So in Schnepphat's vision, as quantum tech matures, this quantum-enhanced convex optimization could really change things.
Yeah, revolutionize scientific discovery, make industries much more efficient, maybe even help tackle some huge global challenges.
It's a pretty compelling picture, isn't it? Taking these weird quantum rules and turning them into practical solutions.
A very compelling vision.
Okay, so let's try and recap our deep dive based on Jürgen Schnepphat's essay. We've looked at why convex optimization is so important.
That guarantee of finding the best solution.
And the exciting possibilities quantum computing brings to the table. We've touched on algorithms like HHL and QAOA.
And their potential for significant speed-ups and tackling problems differently, especially in areas like machine learning, finance, logistics.
But, and it's a big but, we also have to remember where we are now.
Definitely. The field is still very much developing. Those hurdles, hardware limitations, noise, error correction, they're significant and need to be overcome.
Still, the potential to just push the boundaries of what we can even compute is really inspiring. It makes you think, doesn't it? How does optimization affect what you do or what you're interested in?
Yeah.
And how might quantum computing completely reshape those possibilities down the line?
It's a field right on the edge of some potentially transformative changes.
Exciting times.
Our deep dive today was grounded in the insightful essay Quantenvertisere Convex Optimierung by Jürgen Schnepphat.